director of the center, Professor Devashish Bhattacharya. He's a good friend of mine, and also we have conducted so many workshops at Shanti Niketan, earlier also physical as well as online. And I have been a regular visitor to Vishwa Bharati for the last 3-4 years. Before pandemic, after pandemic, I have never been to. So I think some basics of R has already been covered. How to enter a single variable, what do you mean by data frame, and what do you mean by the vector, and some of the basics like graphics, etc. I think these parts have already been covered. I'll not go into the basics of R. R is a very, very important software in the sense because it's a free software and open source software. And moreover, there is a lot of flexibility with R. The reason being because it's now handled by a team of people who are very, very active. And Ross Ihaka and gentlemen, these two people who have invented this R earlier, now it has been taken over by the team. And let me tell you, almost 99% of the universities in US, they are making use of R. Now, the Python is also coming up, as you know, and soon you will be having a workshop on Python maybe next time, because that is also a very, very important part of analysis, and that takes care of structured and unstructured data in a very efficient way. So I will be covering the topics which are very, very important in the sense, because if you are doing any type of research, these topics somewhere or the others will always come into the picture, because like looking at the correlation between two variables, then multiple correlation between more than two variables, and also different other type of correlations which you need to compute from time to time. And moreover, there are regression techniques. So there are many types of regression. Simple regression is there, which involves only two variables. Then there is a multiple regression, which involves more than two variables. And then there is a logistic regression, panel data regression. There are many other types of regression analysis techniques. So we will discuss all this. Now, before coming to the application, how to do analysis in R, I think it's better to have some kind of theoretical background of the topic so that you can understand what is the actual meaning of correlation, what is the actual meaning of regression. So I will share a PPT and then explain you certain theoretical concept before coming to the actual practical demo through R. Hopefully that will be fine with you. And if you face any difficulty at any time point, you are most welcome to interrupt me, and you are most welcome to ask me any question related to the topics which I am covering. Okay. All right. So let me share the screen. Just give me a moment. Hopefully my desktop is visible to you. Can anybody respond, please? Any respondent? Is that visible?
Sir, it's visible. Yes, sir, it's visible.
Thank you. Thank you very much. Let me start with very basics and before moving on to the R. See, my topic will be to cover the part which is called correlation and regression today. This will include simple regression, then multiple regression, stepwise regression. All these things I'll cover today. And then today also we will see how to check the normality of the data. Because tomorrow I'm covering a very, very important topic on estimation and testing of hypothesis, which is also called the backbone of the statistics. So for 2 days, for 4 sessions, you will be with me. And hopefully, if you listen to me carefully, maybe you can learn many things. Of course, you are online. You have a choice just to on your system and move everywhere. But I will not recommend that, because if you have joined this program, you have to be attentive so that you can learn something and you can implement in your future research. Okay. All right. Now, it's very important to, before coming to even correlation and regression, it is very important to understand the nature and types of data. Unless or otherwise you are not clear about the nature and types of data, it is very difficult to conduct any type of research. So first 5-10 minutes I will spend on research methodology part, which are very, very basics. And then I'll move on to the topic of correlation and regression. Okay, nature and types of data. If you look at the nature of the data, any type of data, either it is called a structured data or it is called unstructured data. Now, what do you mean by structured data? Structured data is the one where features can be easily extracted. For example, if I give you 100 observations, say relating to height or weight, you can easily compute its mean. You can compute median, mode, then skewness, kurtosis, minimum value, maximum value, range of the data. Everything can be easily computed. So most of the time, the structured data is in the numeric form. And the features can be, features means mean, median, mode, skewness. All these are features of the data. What do you mean by features? Features means they give you some kind of information about the data. And most of the time, the structured data is in the numeric form. But what happens sometimes, the data may not be exactly in the numeric form, but it's easily convertible into numeric form. That type of data is also comes under what is called structured data. For example, look at gender. The gender is not numeric as such. It's a label, male and female. But I can always assign certain codes, say male as 1, female as 2. So it becomes numeric. And then go for the counting of ones. That means counting, you are counting of males. And counting of 2 means you are counting females. And features like how many males, how many females are there, they can be easily extracted, right? So this kind of data, which was earlier not in the numeric form, but it's easily convertible into numeric form, also comes under structured data. The other examples like religion, I can write Hindu as 1, Muslim as 2, Sikh as 3, Christian as 4, or you can write in any other order. So it's a label but convertible into numeric form. Similarly, locality, you can have rural people, you can have urban people, you can have semi-urban people. So I can write 1, 2, and 3. Socioeconomic class, lower class, middle class, upper class, I can write 1, 2, 3. So all this kind of data, which was in the form of certain labels, is easily convertible into numeric form, also comes under structured data. So what is basically structured data? Either it is already in the numeric form or it's easily convertible into numeric form. This is what we mean by structured data. Then there is unstructured data. What do you mean by unstructured data? Unstructured data is the one where features are not easy to extract. It's difficult. For example, everybody is using WhatsApp. There are hundreds of messages every day, videos, pictures, right? And if at the end of the day, I ask each and every one of you to convert the entire information into numeric form, I don't think it's easy for anyone. But information is there. This kind of data, which is not easily convertible into numeric form, comes under what is called unstructured data. Similarly, if you look at any social media site, Facebook, Instagram, Snapchat, there is a lot of information, but that is not in the numeric form. So this kind of data is called unstructured data. Now, it's easier to deal with structured data, very difficult to deal with unstructured data. And 2 of my students from bioinformatics, 2 from statistics, they have completed their PhD under our guidance only on unstructured data. We have derived certain methods and techniques using some advanced techniques like Dirichlet's integral, machine learning, and artificial intelligence, where if you give us any text or any paragraph, without reading the text, we can tell you in 2-3 minutes what they are talking about without even reading the text. So that kind of data is called unstructured data. Now, people also talk about these days big data. Now, big data is sometimes, and in most of the times, it's basically a combination of structured and unstructured. Some part may be structured, some may be unstructured, right? And for example, people put a lot of comments on Facebook, and after a while, we know person's nature and his interest. So all these things are basically they form, because there are many people, thousands of people are writing their comments. Not only thousands, there are lakhs of people who are writing their comments, right? And obviously, this is referring to what I mean to say is a big data. There may be some numeric form, there may be some part which is not numeric. So this kind of data is called a big data. But as far as this program is concerned, today's program, I will focus only on structured data. Structured data means it's in the numeric form or it's easily convertible into numeric form. So if you look at the structured data, it is basically of two types. Either it is called categorical data or it's called measurement data. Now, what do you mean by categorical data? Categorical data is the one where the measurements are in terms of categories. I have already given you an example like gender. I can write male as 1, female as 2. So simple category can be converted into numeric. Socioeconomic class, lower class as 1, middle class as 2, upper class as 3. So this kind of data where measurements are in terms of categories or 1, 2, 3 form comes under what is called the categorical data. Then what is a measurement data? Measurement data means some kind of instrument is being involved in measuring something. For example, you can measure height, you can measure weight, blood pressure, cholesterol. So you require some kind of instrument. But what happens sometimes you don't require an instrument, but it could be a measurable quantity. For example, to measure age, you don't require any instrument, but age can be measured in years. Then you can add months, even days, minutes, and seconds together. So it becomes a measurable quantity. So hopefully the terminology about structured data, unstructured data, and if you are dealing with structured data, then what do you mean by categorical data and the measurement data is clear to you. Okay, let's look at examples of categorical data. These are examples of categorical data. For example, hair color. Hair color could be brown, it could be red, black. Now, I was afraid of putting white there because people sometimes get depressed. Our entire body is made up of 4 types of nucleotides. They are known as ATGC. I can write A as 1, T as 2, G as 3, C as 4. Similarly, hair color can be written as 1, 2, 3. Eye color, which is black, brown, green, blue, can be written as 1, 2, 3, 4. Gender can be coded as 1 and 2. Disease, mild, moderate, severe, you can write 1, 2, and 3. Genotypes, depending upon which one is dominant, which one is recessive, you can write 0, 1, and 2. So all this kind of data, which was in the form of a certain label, it's easily convertible into numeric form. And this is what do you mean by categorical data. And when we are using the technique of correlation or sometimes regression, or sometimes we will be giving you some idea about one-way Nelson variance, two-way Nelson variance, and repeated ANOVA, etc., which I'll cover tomorrow. They will all require the knowledge of categorical data because there will be using categorical data as well as measurement kind of data. That's why it's important to cover here. So that's all about the categorical data. And now we want to move on to measurement data, like cholesterol. You can have some instrument to measure. Height, you can have some instrument to measure. Age, you don't require any instrument, but it could be a measurable quantity. FPKM value, sometimes we take a part of DNA and put that into alumina experiment. And whenever we conduct this experiment, our entire information of that fragment comes out in terms of ATGC, which are known as nucleotides. And then there is a mathematical formula to quantify that ATGC into some expression. And that expression is basically called FPKM value, which is called fragment per kilogram per million. Then how many genes are expressed for a particular kind of disease? That's also a measurement data. Time to complete a homework assignment, because time is also a measurement. So all these are examples of measurement data. One important point about measurement data, any type of measurement data is basically, it could be of 2 types. Either it is called a discrete measurement data or it is called a continuous measurement data. Now, what do you mean by discrete measurement data? Discrete means if your data takes only certain isolated values, then it's called a discrete measurement data. For example, say number of members in a family. Number of members in a family may be 3 members, 5 members, 7 members. I cannot say number of members in a family is 3.6. It doesn't make any sense, right? Hopefully you understand what I'm saying. Similarly, number of genes expressed for a particular disease. There may be 3 genes are expressed or 9 genes are expressed, but I cannot say number of genes expressed is 8.9. It doesn't make any sense. So if your data is capable of taking only certain isolated values, then it is called a discrete measurement data. And what is a continuous measurement data? Continuous measurement data means it is capable of taking all values within certain specified range. For example, if I say height, say between, I fix 2 ends, say height between 145 to 170 centimeter. Then height can take any value. It could be 157.5, 157.75. You can add third, fourth decimal depending upon the accuracy of your instrument. It could be 162.2 and so on. So it is capable of taking all values within a certain specified range. So this kind of data is basically called a continuous measurement data. So hopefully the difference between the discrete and continuous is clear to you. Okay. Now, before coming to the correlation and regression, so far I discussed that there is a structured and unstructured data. We are focusing on structured data, which means in the numeric form, and it could be of 2 types, either categorical or measurable type of data. I have already given you examples. Now, if you are dealing with the categorical data is in terms of 2 different scales. One is called the nominal scale, another is called the ordinal scale. Similarly, the measurement data is also in terms of 2 different scales. One is called the interval scale, another is called the ratio scale. Why I am discussing these scales? Because many softwares, even in R, even in SPSS, MATLAB, Minitab, Stat Graphics, you need to specify whether your data is a categorical data, and if it is categorical, on which type of scale it belongs to, nominal scale or the ordinal scale. And if it is a measurable kind of data, then it falls to which kind of scale, interval or ratio. So I'll give you a few examples so that to make it clear, and you will not face any difficulty in the analysis. Now, there are 2 scales for categorical data. It's written here, nominal and ordinal. Now, what do you mean by first 2 scales for categorical data? What do you mean by nominal scale? Nominal means if each and every category is given equal weightage. Let me just repeat. If each and every category is given equal weightage, there is no preference of one category over the other, then we say that our data belongs to the nominal scale. For example, gender. Everybody is human being. I can write male as 1, female as 2, or you can write female as 1, male as 2. Doesn't make any difference. It is simply a label, right? Similarly, you can have, let's say, rural and urban. People belong to rural class, people belong to urban class. So it is simply a label. So bottom line is, if there is a equal preference to each and every category, then we say that our data belongs to the nominal scale. Just like religion. I can write Sikh as 1, Hindu as 2, Muslim as 3, Christian as 4, or you can write Christian as 1, Muslim as 2, Hindu as 3, or in any other order. So bottom line here is that if all the everybody is human being, right? So if all the categories are given equal weightage, there is no preference of one category over the other, then we say that our data belongs to the nominal scale. Hopefully, this nominal scale is clear to you. Now, let's move on to ordinal scale. It's again for categorical data, remember? But the difference between nominal and ordinal is that in case of ordinal scale, the categories can be arranged in order from the lowest to the highest, or from the highest to the lowest. For example, socioeconomic class. Say lower class has 1, middle class has 2, upper class has 3. So these categories can be arranged in order from the lowest to the highest. 1 means the lower income group, 3 means the higher income group. Similarly, look at education categories: primary school, middle school, high school, graduate, postgraduate, higher. So all these categories can be arranged in order from the lowest to the highest, right? So this kind of data, which is of categorical in nature, but the categories can be arranged in order from the lowest to the highest or highest to the lowest, comes under what is called the ordinal scale. That's the only difference between nominal and ordinal. You cannot arrange in nominal scale, but you can arrange in ordinal scale from the lowest to the highest. That's all about the nominal and ordinal scale. But whether you are dealing with the nominal scale or you are dealing with the ordinal scale, one important caution, that the numerical distance between any two categories does not have any significance at all. For example, if I'm writing, say, male as 1, female as 2, and subtract 2 minus 1, it doesn't have any meaning at all, right? Similarly, if lower class has 1, middle class has 2, upper class has 3, and subtract 3 minus 1 or 3 minus 2, it doesn't have any meaning at all, right? So whenever we deal with the categorical data, the numerical distance between any two categories does not have any significance at all. That's all about the categorical data. Now, again, for measurement data, there are two important scales, and people get confused between interval and ratio scale. Please try to listen to me carefully. You will not face any difficulty in recognizing the scale. That this is a variable, you will be able to recognize it. This variable belongs to which type of scale, if you listen to me carefully. So there are two scales for measurement data, interval and ratio. Now, what do you mean by interval scale? Now, in interval scale, sometimes the mathematical operations may not be valid. There are many types of data where mathematical operations are not valid. Let me give you an example. Let's say some beauty contest is going on, and say there are judges giving score out of 10. Let's say first person gets a score of 8 out of 10, and second one gets a score of 4 out of 10. Let me just repeat. Some beauty contest is going on. Judges are there who are giving score out of 10. First person gets a score of 8 out of 10. Second one gets a score of 4 out of 10. Divide 8 by 4, answer will be 2. But I cannot make a statement that the person whose score is 8 is exactly twice the beautiful than the person whose score is 4. I cannot make such type of statement. Mathematically, it is not correct. Let's say one student has scored 90 marks in a test. The other student has scored 30 marks in a test. Divide 90 by 30. Answer will be 3. But I cannot make a statement that the student whose score is 90 is exactly 3 times the intelligent than the student whose score is 30. He may be intelligent in sports or in some other category, right? So you cannot make such type of statement. So idea here is sometimes the mathematical operations are not valid. And moreover, in interval scale, 0 does not mean the absence of character. For example, if I say temperature 0, do you think the temperature is absent? It is still better than -5. So 0 has a meaning in interval scale, right? Now, if I say somebody has scored 0 in a test, it does not mean the person is not intelligent at all. Maybe on a particular day, his or her performance is not up to the mark. Next time he or she can score better. So 0 does not mean that quantity is absent. 0 has a meaning. That's why in interval scale, 0 is considered as an arbitrary 0. 0 is considered as an arbitrary 0. It's not the true 0. So I think I have given you enough examples of interval scale. There are problems with each and every scale, and to overcome all such problems, there is a highest rating scale, and that is called the ratio scale. Now, what do you mean by ratio scale? Ratio scale is the one where all mathematical operations are valid, except you have to be very careful about 0. If you come across, let's say, let me give you an example. All mathematical operations are valid in the sense, let's say one person is having weight 90 kilogram, and another person is having weight 45 kg. Now, if I divide 90 by 45, your answer will be 2. Your answer will be 2. But I can always make a statement that the person whose weight is 90 kg is double the weight of the person whose weight is 45 kg. Nothing wrong with that. Generally, we say that age of the father is 3 times the age of the son. If father is 45 years, son is 15 years. So it's 3 times. Nothing wrong with that. So you can divide, you can multiply in ratio scale, which is not possible in interval scale, right? And moreover, in ratio scale, 0 is a true zero. 0 stands for that it is a true zero. What do you mean by true zero? True zero means quantity does not exist. For example, if I say height 0, that means it doesn't exist. If I say weight 0, it doesn't exist. If I say age 0, it doesn't exist. So hopefully I have given you enough examples of all these scales: nominal, ordinal, interval, and ratio. First two scales are for categorical data. Next two scales are for measurement data. Please try to remember all these things about these scales. Now, if you have any question up to this, that completes your research methodology part. Now I'll move on to the actual topic of correlation and regression. If you still have any question, you are most welcome to ask. Yes, please. Any question about these scales or types of data? Or everything is clear? Anybody can respond, please. Do you have access to unmute yourself?
Clear, sir.
Yeah, clear. If anybody is having any doubt, they can
No
still
doubt,
ask
sir,
question. Everything is clear. Okay.
Yes.
Am I audible to all? And most of the things, I mean, if I'm going very fast, I can be a little bit slow. If I'm slow, I can be a little bit fast.
And this
What
is
do you
perfect.
think? Or this is okay. All right. Let's move on to the topic, a very, very important topic in statistics, that is called correlation and regression. So there are two words here. The first word is correlation. The second word is regression. Now, what do you mean by correlation? Correlation means you are simply looking at the relationship between two variables, or sometimes more than two variables. You are simply looking at the strength of relationship between two variables or more than two variables. Remember, correlation is never used for prediction. I'm making a very strong statement. Correlation is never used for prediction. It just forms a part of prediction. The second term, which is called regression, basically stands for how to predict. So correlation is never used for prediction, but regression is used for prediction. So I'll explain you I will take you to the journey of all different type of correlation and regression techniques. Now, before moving on to regression, first of all, we go through the correlation part, and then I'll move on to regression. And in the second part of the session, I'll give you a practical demonstration how to compute correlation, how to compute regression, all these techniques using R. All right. So first, I will look at correlation. There are different type of correlations. Where to use which type of correlation, you have to be very much clear. And I'll try to give you, although I'll not give you any mathematical formula. There is a mathematical formula to compute each and every correlation coefficient. And if I go into mathematics, then none of you would like to listen to me. I will just tell you the practical situation where this kind of correlation is applicable, and that will make more sense. All right. So these are different type of correlations. If you see carefully, the first important type of correlation is called Curl-Pearson's correlation coefficient. Sometimes this is also called product moment correlation coefficient, because it is based on the product of certain two variables, in fact. Now, its symbol is small r. Whenever we compute Curl-Pearson's correlation coefficient, we always write small r, its value. That small r is 0.8 or 0.9, whatever. And the limits for this r, it always lies between -1 to +1. It cannot be below -1, it cannot be above +1. So limits for r formula is designed in such a way that r will always lies between -1 to +1. So if you are making certain calculations and computing the value of r, and it gives the value as 2.69, that means you are absolutely wrong. It cannot be 2.69 because its limits are from -1 to +1. If your value of the correlation is coming out to be negative, then the two variables are negatively correlated. What do you mean by negatively correlated? If you increase the value of one, the other is decreasing. This is what we mean by negative. And if the value of R is coming out to be positive, like 0.6 or 0.5 or 0.7, then you will say that correlation is positive. Positive stands for that if value of one variable is increasing, the another variable is also increasing. This is what we mean by positive correlation. Now, where to apply this type of correlation? Very important. Number one, you can note down few points. It's not possible to write each and everything on the PPT. Number one, where to apply Karl-Pearson's correlation coefficient? So first point, both y and x, it's computable only for two variables. Karl-Pearson correlation coefficient you can compute only for two variables. One variable is x, another one is y. But the condition is that both of them, they should be measurable quantities. Measurable means metric quantities. Both, the like correlation between height and weight. Height is measurable, weight is measurable. Correlation between age and blood pressure. Age is measurable, blood pressure is measurable. Correlation between prices and consumption. Consumption quantity is measurable, prices are measurable, right? So if this is the situation that both y and x, they are measurable quantities, that's the first condition for Karl-Pearson correlation coefficient. What is the second condition, which is the most important? That if you plot x along x-axis, y along y-axis, then the diagram of dots which you obtained for each and every pair of y and x, they must follow a straight line. Then and only then Karl-Pearson correlation coefficient makes sense. And this type of, if they follow along a straight line, this type of relation is called a linear relationship. Linear means along a straight line, means linear. We used to study in 10th standard the equation of a straight line. Y is equal to mx plus c. That is the equation of a straight line, where c is the intercept, m is the slope, right? Now, so two important points for Karl-Pearson's correlation coefficient. Number one, both y and x, they should be measurable quantities. Number two, there should be linear relationship between y and x. That's all. If these two conditions are fulfilled, then you can apply Karl-Pearson's correlation coefficient. But it may not be necessary that you always apply Karl-Pearson. It may happen that when you plot x and y, sometimes it is increasing, the curve is increasing, or the points are increasing. After that, it start decreasing. Then after a while, it will start increasing. Then in such type of situation, Karl-Pearson correlation coefficient will not work. Do not compute Karl-Pearson correlation coefficient, right? Hopefully this makes sense to you. Right. Number two, the second type of correlation is called Spearman, and we are going to compute all this using R. Spearman's rank correlation coefficient. Now, what do you mean by Spearman's rank correlation coefficient? First of all, it is denoted by rho, RHO. And this is the symbol which I have written. This symbol is rho, RHO. Again, this rho value always lies between -1 to +1, just like small r. Small r lies between -1 to +1. And rho also lies between -1 to +1. Now, what are the conditions to compute Spearman's rank correlation? Now, what happens sometimes, we are dealing with categorical type of data. Let's say there is a questionnaire, and questionnaire is having different questions. They are on 5-point scale. Strongly disagree to strongly agree. 1 to 5 scale. You know Likert scale, right? 5-point scale or a 7-point scale. Strongly disagree to strongly agree, or very unsatisfied to very satisfied. So you must have gone through such type of questions, and they are on 5-point scale or a 7-point scale. Now, you have the responses of the people, and 1 to 5 scale. 1 to 5 means 1 means the lowest, 5 means the highest. For example, very unsatisfied, lowest. Very satisfied, highest. So data is in the form of ranks. Data is in the form of ranking. So if the data is present in the form of ranking, then obviously you will compute. You cannot compute Karl-Pearson's because x and y, they are not measurable quantities. They are in the form of ranks. Then we compute what is called Spearman's rank correlation coefficient. Then we compute Spearman's rank correlation coefficient. That is the first condition, right? So if the data is in the form of ranks, we compute Spearman's rank correlation coefficient. Similarly, you can look at some beauty contest is going on. Judges are giving, so one judge is giving, let's say 10 participants, that this comes at number 1, this comes at number 2, this comes at number 3. But second is having different opinions, but their opinions are being given in the form of 2 columns, that these are the opinions and names in the first column, that maybe it may happen that first contestant, the given rank is 2 by the judge 1, but it is given rank 1 by the judge 2. It can happen. Their opinion can differ, right? So if this is the situation, we are going to apply Spearman's rank correlation. Another situation to apply Spearman's rank correlation is even if both y and x, they are measurable quantities. They are not ranks, they are measurable quantities. But if I check the normality of y, normality of x, and today we will go through how to check the normality of the data. If you look at the histogram or a box plot, you can check the normality of the data. And if the shape of the histogram of x or y is not symmetrical, then obviously it's a non-normal data. Even when y and x, they follows non-normal data, it's not advisable to compute curl Pearson. Let me just repeat. It's not advisable to compute curl Pearson. Even y and x, they are measurable quantities, but they are non-normal. It's better to go for Spearman's rank correlation rather than curl Pearson's correlation coefficient in that case. Data is already in the form of ranks, you can apply. But if y and x measurable, they are not following a normal distribution, even in that case, it's better to go for Spearman's rank correlation. Remember, curl Pearson, Spearman, they are applicable to the situation when there are only 2 variables, y and x. There is no third variable at all, right? Then there is a third type of correlation, and that is called multiple correlation coefficient, generally denoted by R square, which sometimes is also called coefficient of determination. And since it is a square, R square can never be negative. So value of this will always lie between 0 and 1. R scale will always lies between 0 and 1. Now, where to compute such type of correlation? This is the situation where you are dealing with more than 2 variables. So in computation of the multiple correlation, there is one dependent variable. It depends upon number of factors. One dependent variable depends upon number of factors. Then we compute multiple correlation coefficient. For example, one variable is y, and y depends upon x1, y depends upon x2, it depends upon xk, k number of variables. But the important point to remember in multiple correlation is, you can note down also that all y, x1, x2, xk, they have to be measurable quantities. If any one of them is categorical, let's say x2 is categorical, gender like male and female, you cannot compute multiple correlation. It's rural and urban, say x3 is rural and urban, you cannot compute. You can compute, or you can apply multiple correlation coefficient only to that kind of data where y as well as x1, x2, xk, they are measurable quantities, or they are metric variables. Let me give you an example of multiple correlation. Let's say yield of a crop. Most of you are from economics, you know. Yield of a crop. Yield of a crop depends upon number of factors. It depends upon amount of fertilizer used, that is x1. Amount of rainfall, that is x2. Amount of seed used, that is x3. The soil fertility, x4. So it depends upon number of factors. Y is the yield of a crop. So yield of a crop depends upon number of factors. Then in that situation, if I'm just computing the relationship between y and x1, x2, xk together all of them, then that type of correlation. So it's basically give you strength of relationship between y and x1, x2, xk, all of them taken together. then this type of correlation is called multiple correlation coefficient. In economics, we are looking at production of certain quantity, and production depends upon number of factors. They can be x1, x2, xk. Growth rate depends upon number of factors, x1, x2, xk. So in all such type of situation, we compute what is called multiple correlation coefficient. Hopefully this makes sense to you. Then there is another important type of correlation, and that is called partial correlation coefficient. That is called partial correlation coefficient. Now, where to use partial correlation coefficient? Partial correlation coefficient is important to compute for the situation where you are simply computing the correlation between two variables, but there may be third variable which can indirectly affect the relationship between the two. I'm just trying to understand what I'm saying. I'm saying that there are, let's say, three variables, x1, x2, x3. I'm just interested to look at correlation between x1 and x2, but this x3 variable can indirectly affect the relationship of x1 and x2. Let me give you an example. Let's say somebody give you the data related to age and blood pressure. All right. And you look at the scatter plot, age along x-axis, blood pressure along y-axis, points are increasing. You will compute Pearson correlation coefficient because age is a measurable quantity, blood pressure is also a measurable quantity. Right? Nothing wrong with that. But you are making presentation somewhere, some doctors are sitting, and one of the doctor is asking you a question, whether there were smokers and non-smokers also in your group, in your data. Now, you haven't checked the status of smoking. And clinically, it is tested that those who are smokers, they are likely to have high blood pressure as compared to those who are non-smokers. And you have completely ignored the effect of smoking. Now, smoking can play a very important role. Now, whatever the correlation you are getting, it could be effect of smoking only between x1 and x2, right? So that means to actually find out the relationship between x1 and x2, that means age and blood pressure, you need to control the effect of smoking. You need to control the effect of smoking. And if you compute such type of correlation, then that type of correlation is called partial correlation coefficient. So 1, 2.3 means that you are looking at correlation between 1 and 2, between x1 and x2, by controlling the third variable, that is x3. It's not that you always control one variable. You can control even fourth variable, x4. Then the notation will be R1 2.34, that by controlling the effect of third and fourth variable, right? So this is what we mean by partial correlation coefficient. Now, then we move on to what do we mean by correlation ratio. Now, it is not necessary that when we plot x on x-axis, y on x-axis, points will be along a straight line. Points may be along a curve also, right? It could be along a curve. And if they are along a curve, Pearson, Spearman, multiple, etc., that doesn't make any sense at all. Not at all. So in such type of situation, if there is a curvilinear type of relationship, we compute another correlation that is called correlation ratio. So we generally compute correlation ratio if there is a curve type of relationship between the variables. Now, sometimes when you look at the scatter plot, the points are neither increasing, they are not decreasing, they are not along a curve even. You never come to know what will happen. Now, you can only rule out the possibility that there is no curvilinear relationship, there is no linear relationship. But there could be any other type of relationship which you are not aware of. And such type of relationship are studied through an important technique of statistics, and that is called non-linear correlations, which is beyond the scope of this program. They are known as non-linear correlations. Okay, so these are some of the important correlations I mentioned. Now, what is the situation of a positive correlation and Pearson's correlation coefficient? Let's say I plotted height along x-axis, weight along x-axis. This is a scatter plot of points. And you can see that points are increasing. And when the points are increasing, obviously you will expect a positive correlation. So you will say that correlation is positive between height and weight. When height will increase, weight is also likely to increase. And there is a positive correlation between height and weight. And height is a measurable quantity, weight is a measurable quantity. You can go for Karl-Pearson correlation coefficient. Let's look at prices and consumption. So here is prices along x-axis, consumption along y-axis. And here you can see points are decreasing. Because when prices will become high, consumption will go down. When the onion prices in India, they are above 100 rupees or 150 rupees, people start to consume less onions. So points will decrease. If you increase the prices, consumption will decrease. And this type of correlation, that means one variable is increasing, other is decreasing, is called a negative correlation. Again, prices measurable, consumption measurable. So you can compute Karl-Pearson's correlation coefficient. But the important point is points are along a straight line. If points would have been along a curve, do not compute Karl-Pearson's correlation coefficient. So that is the situation. Now look at this diagram. This is also a scatter plot. This scatter plot, there is no linear trend. I cannot say points are increasing or decreasing. I cannot say points are lying along a curve also. Right? So I can only rule out the possibility that there is no linear relationship between the variables. What are the variables? Blood pressure along x-axis, hemoglobin along y-axis. That is called HB. Right? Now, clinically also, there is no relationship between blood pressure and hemoglobin. I cannot say that those people who are having high blood pressure, they are likely to have low hemoglobin or high hemoglobin. I cannot say that. So that's why the trend is coming out to be like this. So here I can only rule out the possibility that there is no linear relationship. There could be any other type of relationship which I'm not aware of. And those are studied with the help of non-linear correlations. But this,
excuse me, sir.
Yes, please.
Sir, can we say it zero correlation?
Zero correlation in the sense of linear only. Because it's in the sense of linear. If you compute Karl-Pearson, value of correlation is coming out to be close to 0 or 0, you will say that there is no linear relationship between blood pressure and hemoglobin. Obviously, you will say. But use the word linear. Use the word linear because Karl-Pearson will give you an idea only about the linear relationship between the two variables, not any other relationship. You follow my point?
Yes. Sure.
All right.
Thank you.
Any other question? Any other question? All right. Now, these are not the only type of correlations. These are the correlations which you have studied in books. These correlations you have studied in books like Spearman's rank correlation, Karl-Pearson, and multiple correlation. But I will take you through the journey of another correlations where many of the statistics people economics people are not aware of. Now, what are these? These are called measures of association. These are called measures of association, and they are used in different situations. Now, so far, if you remember, we have discussed about nominal scale and ordinal scale for categorical data, interval and ratio for the measurement data, if you remember. Now, if one of the variable is nominal, X is nominal and Y is also nominal. Let's say one variable is gender, male and female. I can write 1, 2, 1, 2, etc. It's a gender. And another variable is blood groups, O positive, A positive, A negative, etc. That is also nominal. And you want to see the correlation between the gender and the blood groups. Now you cannot apply Karl-Pearson. You cannot apply Spearman's because data is not in the form of ranks. You cannot apply multiple because there are only two variables. Now, which type of correlations are applicable then? If this is the situation, nominal by nominal. Nominal by nominal stands for one variable is on a nominal scale, like gender. Another variable is also on a nominal scale, like blood types. Then which type of correlations to be computed? These are the correlation which I listed. Contingency coefficient, phi and Kramer's V, lambda coefficient, uncertainty coefficient. And out of this, uncertainty coefficient is the best one. Out of this, uncertainty coefficient is the best one. The people from economics or statistics, they generally make mistake. What they generally do, whenever there is a categorical data, it's a categorical data. One variable is nominal, another is also nominal. They make a frequency table of 2 by 2 or 2 by 3 and then compute chi-square. This is what chi-square is a gold standard. For large samples, they compute chi-square. If there is a small sample, then there is substitute of chi-square that is called Fisher's exact test. People also do that. But absolutely wrong. Absolutely wrong. Why wrong? Let me give you the reason also. Because chi-square can never be negative. It will always give you a positive value. And you will never come to know whether the association between the two variables is negative or positive, because you are getting the positive value only. But if you compute the uncertainty coefficient, you may get a positive value, you may also get the negative value. So that is the advantage. Do not compute simply chi-square. Another situation is ordinal by ordinal. Let's say one variable is ordinal, another variable is also ordinal. Examples: level of satisfaction, very unsatisfied to very satisfied, very unsatisfied to very satisfied. So it's ordinal. You can arrange the categories, let's say 1 to 5 scale. You can arrange the categories in order. That's one variable, ordinal. Another variable is given income. Income in the form of categories. Let's say less than 10,000. Those people who are having less than 10,000, category 1. Between 10 to 20,000, category 2. 20 to 40,000, category 3. And more than 40,000, category 4. So it's again ordinal. So ordinal by ordinal. Income versus level of satisfaction. So ordinal by ordinal. In such type of situation, do not use again chi-square. There are methods. We compute gamma coefficients, Sommer's D, Kendall-Stock. But out of this, gamma is the best one. It will give you a negative and positive value also. And you will come to know whether the association is positive or association is negative. Of course, when one variable is nominal, another is ordinal, you can apply chi-square. Let's say one variable is gender, which is nominal. Ordinal variable is your socioeconomic class, lower class, middle class, upper class. They can be arranged in order, so ordinal. In such type of situation, you can use chi-square, no problem with that. And if you have nominal by interval or ratio, nominal by interval or ratio, one and the same thing. Nominal means just like gender. Interval means blood pressure. It's on interval scale. Or a temperature, an interval scale. Nominal, let's say gender. Right? In such type of situation, again, do not use chi-square. There are other correlations like kappa, risk, McNemar, out of biserial correlation. Eta coefficient is the best one to compute. Eta coefficient is the best one to compute. So remember, this is a very, very important slide. And generally, most of the books, they do not cover this aspect of correlation. But this is very, very important. Whenever, if you are a researcher, then you should be clear about where to use which type of correlation. Okay. Let's move on to the next part. These are examples. For example, nominal by nominal. What is the example? Gender versus blood types. Gender is nominal, blood types are nominal. Then you have ordinal by ordinal. Ordinal by ordinal, like paternal age versus risk of disease. Risk of disease is mild, moderate, severe. It's ordinal. Paternal age, you can have 20 to 30 years. Then next category is 30 to 40 years, then 40 to 50 years. So ordinal by ordinal. You can use gamma coefficient or Sommer's D, or out of this gamma is the best one. Then nominal by ordinal. You can apply chi-square or Fisher's exact test. Nominal means like AMD. AMD means age-related macular degeneration. Either the person is having or not having, so it's nominal. And the risk of the disease, like mild, moderate, severe, it's ordinal. So nominal by ordinal. You can compute chi-square or Fisher's exact test. If your sample size is large, use chi-square. Sample size is small, use Fisher's exact test. Then nominal by interval and ratio. Like ethnic origin is nominal. Person is Asian, African, American. That is ethnic origin. Versus amount of lactase produced in the intestine. That is some measurable quantity, interval scale. Right? Everybody's pancreas is creating amount of lactase, and that can be measured. So ethnic origin versus amount of lactase, whether Asian produce more, whether African produce more, or American produce more, something like that. Okay, so if this is the situation, then you have nominal by interval, and here we are going to compute eta coefficient, the best one. Of course, kappa, risk, McNemar, others can also be computed. Of course, whenever we have the last category, ratio by ratio, height versus weight, age versus blood pressure, you have a lot of choices. Go for Curl-Pearson, Spearman, partial, multiple. So all these things can be computed. So these are examples. Yes, please. So this slide I have already explained. The correlation lies between -1 to +1. If there is a correlation of exactly value of -1, that means X and Y are perfectly negatively correlated. What do you mean by perfectly negatively correlated? That means if I'm increasing X by 5 units, Y is also changing by 5 units. Exactly the same units have changed. Similarly, what do you mean by positive? If I'm changing X by 2 units, Y is also changing by 2 units at each and every step. That's a situation of a positive correlation. And when we say 0, 0 means there is no linear relationship between the variables. All right. Now, where to apply? Where to apply Curl-Pearson's correlation coefficient, or where to compute Curl-Pearson's correlation coefficient? Now, if you see the points here, points are along a straight line. Here also, but it is increasing. You will expect positive. Here you will expect negative. Points are decreasing. So where to compute Curl-Pearson's correlation coefficient? If this is the situation or this is the situation on the left-hand side of this line, because they are linear relationship. But look at the other side of the line. You have a curve. Here you have a curve, right? So there is no linear relationship between Y and X. And people also compute Curl-Pearson, and the value will come out to be about 0. And they say that there is zero correlation between that. Absolutely wrong. Because you can say there is no linear relationship between the variables. That's okay. Answer is correct. But there could be quadratic relationship. There could be cubic relationship. There may be exponential type of relationship. You cannot rule out the possibility of the other relationships. So that is the idea of linear and non-linear type of relationships. Now, what is the idea of a strong and weak relationship? The idea of strong and weak relationship is, if you see this, the points are increasing. Points are increasing. And here also points are decreasing. But if you see carefully, on the right hand side, here also points are increasing, here also points are decreasing. But if you critically evaluate, these points are very, very close to each other. They are concentrated. And if you drop a line from the center, points will be very, very close to that line. If points are close to the line, then we say that there is a strong relationship. So in this case, positive strong relationship, in this case, negative strong relationship. Of course, here also you can compute Curl-Pearson, but it will give you a weak kind of relationship. Maybe correlation Curl-Pearson will come out to be value of 0.5, 0.6. And this will be -0.5, -0.6. And here it could be correlation like 0.8 or 0.9. Here also -8 or -0.8 or -0.9, etc. Right? So that is the idea of weak relationship and strong relationship. If points are close to the line, they are concentrated, strong, you can expect strong relationship. points are far away from each other, you will expect weak relationship between the variables. So Pearson correlation coefficient, I have already explained. Spearman's rank correlation coefficient, I have already explained. Partial correlation coefficient, multiple correlation coefficient, all these things I have already explained. Like multiple correlation coefficient, one variable depends upon number of factors. For example, blood pressure may depend upon age, it may depend upon weight, it may depend upon body surface area, stress, etc. So blood pressure is a dependent variable. Age, x1 independent, x2 weight independent, body surface area x3 independent, stress level x4 independent. So y depends upon x1, x2, x3 and x4. Compute multiple correlation coefficient because age is a measurable quantity, weight, body surface area, stress level and blood pressure, they are all measurable quantities. Partial correlation already explained. Correlation between the two variables by controlling the effect of other variables. Okay, that's all about the correlation. If you have any questions in the theoretical part of correlation, yes please, you are most welcome to ask. Yes please, any question in correlation so far?
Examples made things very easy, sir, to understand.
Yeah. You are from which place?
From Sikkim University.
Sikkim University. Very nice.
So I have a question.
Yes, please.
Some I study in the effectiveness of nutritional counseling. So my data is in two form, pre and post. So which type of test I will use for this?
See, in pre and post test, you are not going to compute correlation, not at all. In pre and post, you are just looking at what is the improvement from pre to post. Is that okay? Yes or no?
Yes, sir.
So that's a problem of paired t-test, which I will be covering tomorrow. And I'll explain you. If there is a pre and post, before giving the treatment and after giving the treatment, you are looking for the improvement, whether the medicine is effective or not, or the training is effective or not, or the nutrition is effective or not. It's not a problem of correlation then. Problem of correlation comes when there are two different variables and you want to correlate, like height and weight, age and blood pressure, prices and consumption. So like this, then we compute correlation. Pre and post, generally we look for the differences. You follow my point?
Yes, sir. So which type of test in my study?
Paired t-test. Depending upon the situation, if your data is following a normal distribution, then you can apply paired t-test. And if data is not following a normal distribution, which I'll discuss today, how to check the normality of the data, then we have to go for the non-parametric test. And that non-parametric test is called Wilcoxon matched pair signed rank test. So you have to apply that for post and pre situation. Yes, please. I'm happy that you have asked some questions. Any other question? Before I move on to regression, please. Yes, please. Any other question? Or everything is clear? Yes, please. Sir. Okay, very good. So should I move on to regression now? I'm just giving you a theoretical background, and then because once you know the theoretical background, where to use which one, interpretation will become easy and you will be very much aware of whether you have computed the right type of correlation or not, right? So in your syllabus, it has been mentioned that you have to compute Pearson, Spearman's, partial correlation, etc. So I'll discuss all this. Of course, categorical type of data we will not discuss here, but they are also available in R. All right. So I have explained you all different type of correlations. And in this session, it's going to be theoretical, and the second part is going to be practical, where you will learn how to compute all these correlations by taking some data and using R. Okay. Now let's move on to regression. Now there are different type of regressions, but we will, in this tutorial, we will study only two types: simple regression and multiple regression. Simple regression and multiple regression. Okay. Now, question is, What do you mean by my simple linear regression? Simple linear regression means there are only two variables, y and x. That's it. One variable is called dependent. Another variable is called independent. For example, this is the model. Y is a dependent variable and it depends upon x. Now, if you remember in our 10th standard or 9th standard, we used to have equation of a straight line. Equation of a straight line was y is equal to mx plus c, where c was intercept, m is the slope. This is the same equation. You can see y is equal to mx. This is your mx plus c. C is your beta naught, m is your beta 1, and x is already there and y is there. So y is equal to, you just read like this, y is equal to mx plus c. But whenever we defined a statistical model, there is always some kind of error. And that is called a measurement error, which is beyond your control. And we always write the model as y is equal to mx plus c plus epsilon. I will explain you what is the meaning of this error. Now, what do you mean by measurement error? Let's say I take 2 kg of milk from a vendor. I went to a sweet shop and that sweet shop person is giving me the milk, and he is having a measurable instrument and he measure and give me 2 liters of milk. Now, next time, this is 1 packet of milk. Next time I say you make another packet of 2 liters, and he also does the same thing. Now, there is no intention, but if you compare these 2 packets, one is having 2 liters, another is also having 2 liters, there may be a little bit of error, maybe 5 grams, maybe 10 grams. Yes or no? Can you answer this? Yes or no? Or they are going to be exactly same? Yes, please.
Yes, sir. There'll be difference.
There will be a little bit, maybe very small, but likely to be, which is beyond your control, And that type of error is, we always write epsilon. Hopefully you understand the meaning of epsilon, right? So whenever we define linear relationship between 2 variables, we always write the model as y is equal to beta naught plus beta 1x plus epsilon, because this is called error. Here I have written error term. Y is a dependent variable, x is an independent variable. Now, whenever we are given some data, these 2 unknown coefficients, beta naught and beta 1, they can be estimated from the given data. And you will get the exact value of this, numeric value of this. Error in that case will go to 0, and you will be left with, let's say, estimate of beta naught is beta 1 hat. Estimate of beta naught is b naught. B naught is now obtained from the data, and estimate of beta 1 is b1. B1 is obtained from the data. Error will go to 0. So you will be left with y is equal to b naught plus b1x. Now you give any b naught and b1, they are known to you. You give any value to x, you can estimate y. Hopefully this makes sense to you. Let me give you a very simple example of a simple linear regression. Now let's say I enter a class. There are 30 students in the class. Now, if there are 30 students in the class, I am having a measurable tape with me and also having a weighing machine, right? Let's say y stands for weight and x stands for height. There are 30 students, but on that particular day, 2 of them are absent. But there are 28 who are present. So I call each and every one, measure the height, measure the weight. Height is your x, weight is your y. So how many observations I'll get? 28. 28 y observations. 28 corresponding means y1 x1, y2 x2, same person. Same person's height, same person's weight. Same person, second person's height, second person's weight. So I'll be getting 28 observations. Yes? So I'll get 28 observations. Now, based on these 28 observations, I look at the scatter plot. I plot, let's say, height along x-axis, weight along y-axis, points are along a straight line, and if points are along a straight line, that means they are following a linear relationship. And linear relationship is this: y is equal to beta naught plus beta 1x. Now, this beta naught and beta 1x, they can be obtained, their estimates can be obtained from 28 observations. And let's say value of beta naught is 3.4 and value of beta 1 is 4.9. So these two values are known to you. So your equation will be y is equal to 3.9 plus 4 point something into x. Error will go to 0. And that, how to make error 0? That is a method of mathematical principle, which is called method of least squares. The method of least squares consists in minimizing the error. So error will go to 0, right? And that will give you an estimate of beta naught and beta 1. Now, once the value of beta naught and beta 1 known, now I have an equation with me. The equation is with me when I enter the class next day. Now, those students who were absent, now they are present. But somehow weighing machine is not with me. But somehow I can measure their height. I call the first one who was absent, measure the height. Height is your x, and substitute in this equation. I know beta naught, I know beta 1 from 28 observations. So error will go to 0. So I put the value of the height, you will get the value of the weight for that person without weighing machine. Without weighing machine. Similarly, call the second person, measure height in centimeter, put the value here, you will get the weight of the second person without weighing machine. So this is called estimation or prediction, right? So without weighing machine, you will be able to get the value of the weight. So this is what we mean by regression. Regression is used for prediction. You are watching television. There is next day's forecast. Chances of rain this much, thunderstorm this much. From where it comes? It comes from regression. It also, of course, not simple regression like this. So there are different type of regressions which we use for prediction of such type of environmental predictions. And you are getting, it's a result of regression. Hopefully, what we mean by simple linear regression is clear to you. There are only two variables, y and x. You want to predict y based on x. That's all. This is the problem of simple linear regression. So once this is the entire interpretation of this equation. This is called a dependent variable. This is called intercept. This is called slope. And this is called independent variable. And this is an error. Random error, which is beyond your control. Right? This is beyond your control. I have already explained you. So this forms the linear component which we have studied in our 10th class. Y is equal to mx plus c. But there we were not including error because we are talking about a straight line. If there are all the points, let's say all the points are on the straight line, there is no error then. Now, what do you mean by this error? Here is you can see the very clearly. Let's say I plot x along x-axis, y along y-axis, and this is the scatter plot. There are 6, 7 points here, right? So what do you mean by now how I have drawn this line? This line is called, green line is called line of best prediction. Now suppose based on these points, 6, 7 data points, I can estimate beta naught and beta 1. And estimate will look like this. I know this is an estimated value, this is an estimated value of beta naught and beta 1. Now you give any value to x, you can estimate y or predict y. To draw a line, how many points you require? You require only 2 points. I take one value of x, you will get one value of y. You take another value of x, you will get another value of y. And then draw this line, green line. Take 1 point here, take 1 point here, and draw this line. This is the line. This line is called line of best prediction, which is crossing through the maximum number of points. Do not draw it manually. It's based on mathematical principle, right? Okay, then what do you mean by this error? For example, this point is almost on the line. If this point is almost on the line, error for this point will be minimum or close to 0. It's almost 0. But look at this one. This is slightly away from the line. So error for this will be this much. Similarly, this point is far away from the line. Error for this point will be high. For each and every point, there will be error. If your points are very, very close to the line, green line, there will be very, very small error. If all the points are exactly on this line, there will be no error. But this will never happen in practical situation. You are likely to have error. And these are called, we need to control these errors. So this is basically the predicted value and this is the observed value. So this is the observed value actually, and this is predicted value. This green line, whatever the value is there on the, for example, for this point, this will be the actual value, this will be the predicted value. And the difference between actual value and predicted value is called residual. It's called residual. Now, what do you mean by slope and intercept? If you're drawing this line, which is based on your regression line, this green line is called regression line. Wherever it is going to cross y-axis, so this is crossing the y-axis at this point, then you measure the distance from origin to this point. This is called intercept. This distance is called intercept, beta naught. What is a slope? Slope is nothing but you drop from anywhere, you drop a line parallel to x-axis, then whatever this angle is being formed, this angle theta is formed, that will give you slope, and you can compute the value of beta 1. Beta 1 is something like tangent inverse, some completed formula is there, but that is in terms of beta 1. You can get the value of beta 1, and that is called the slope. If this would have been more steep, slope would have been high. If this would have been flatter line, slope will be less. So there are two things only, intercept and slope, right? So hopefully this diagram makes you each and everything clear. Yes, please. Is this clear? Anybody can respond?
Yes, sir, it is clear, but sir, I have a question.
Yes.
Sir, in previous example, you give the example of a height of 30 students. That
Right.
on a particular day, you have height and weight,
Yeah.
28 students and 2 are missing. On
Yeah.
the next day, you can measure,
Height.
you were able to measure the height of the 2 students. And that
Mhm.
was x in that particular equation.
Yeah, that is x. You substitute
Yeah.
the value of x, you will get y for that person.
Yeah.
And similarly
Yeah,
for the
yeah.
second one, you will get y. Yeah.
But in that particular example, what is the B naught and beta 1? And the example that
B
you
naught,
said,
B naught is an estimate of this beta naught.
it
B
is
naught
actually
is an estimate of this beta naught. B1 is an estimate of this beta 1. How to get this estimate? I have written here.
Yes.
The unknown coefficients beta naught and beta 1 are estimated
Yes.
through the data by using method of least squares. So there is a principle of least squares. We minimize the error sum of squares. Actually, are you from mathematics? I can explain you a little bit. If you are from mathematics,
sir, I have studied MS
Okay.
Economics.
just listen to me then carefully. How we
Okay,
get the
thank
estimate. Now, what will be the value of epsilon I from here? Your epsilon I will be, you take all the factors on the other side. Okay. Then it will be y naught minus beta naught minus beta 1 xi. That will give you epsilon I. Is that okay? Yes? No.
Yes, sir.
So if I want to compute epsilon I from here, how will I compute? Yi minus, you take on this side, yi
Yes.
minus beta naught minus beta 1 xi. Right?
Okay.
Now,
Yes, sir.
you will get epsilon I. Now, you square this quantity, epsilon I square. You take epsilon I square. So you're on the right hand side, you will get
The left hand side.
yi minus beta naught minus
Yes.
beta 1 xi square. Okay, you will get square
Okay.
on both sides. Then take the sum. Sum stands for this sum, single sum. So you know summation. So summation of epsilon I square. So you on the right hand side, you will get summation of yi minus beta naught minus beta 1 xi whole square. Is that okay?
Yes, sir.
Yes. Right. So you will get that quantity. Now, once you get that quantity, there is a mathematical principle that if I differentiate that quantity with respect to beta naught, and put equal to 0. Differentiate that quantity with respect to beta 1, put equal to 0. You will get two normal equations. And normal equations will be in your 8th standard, 9th standard. We have such type of questions. 7x plus 8y is equal to 9. Second equation was 8x plus 5y is equal to 10. Then we used to solve these equations by multiplying the first one and the second one with something to get the values of x and y. Yes or no?
Yes, sir.
Same thing will happen here. You are getting two equations in terms of beta 1 and beta naught. So solve those equations for beta naught and beta 1. They will give you the value of x and y. That means beta naught and beta 1. And once you get those values, you will get this equation.
Okay.
That is the idea. So give any value to x, you will get y. So
Thank you,
this
sir.
principle is there. Is that okay?
Yes, sir.
Okay. So this is called simple linear regression. Any question, any other question in simple linear regression? Yes, please. I request everyone to mute, please. There is some disturbance going on, little bit. If you have any question, you can ask me in simple linear regression, because now we are left with half an hour, and then we will be having a break. And after that, I'll move on to straight away move on to correlation in R, how to compute all these things in R. Any question up to this? No question? Should I move on? No response. Can anybody respond, please?
Excuse me, sir. We are always talking about the regression, to regress one
variable on the other.
Yeah,
To regress one variable on the other.
By regress mean that we are
you want to predict one variable for given value of the other
one.
variable.
Yes,
Yeah.
sir. Thank you so much, sir. The
Absolutely.
essence is clear now. Yes.
Okay. Now we move on to multiple regression. What is a multiple regression? This is the last slide, and then of course I'll give you some questions and all these things. Now, what is a multiple regression? Multiple regression is an extension of simple regression to multiple variables. In simple regression, we have only two variables, y and x. Y depends upon x. Y is called dependent variable, x is called independent in simple linear regression. But here, as I already explained in correlation, there is one variable y, which is a dependent variable. It is a measurable quantity. And then there is a set, which is this x is called a vector, or it includes independent variables or set of k independent variables. They are written as x1, x2, xk, set of k independent variables. But the question is, they all have to be measurable quantities. Y is measurable, x1, x2, xk, they are all measurable quantities. Now, based on this, we again form an equation. What is that equation? Yi is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk, because there are k independent variables, plus some epsilon, that's uncontrollable error, right? And you are dealing with n number of observations. You are dealing with n number of observations. We again apply method of least squares. And we will get the estimates of this. So estimate of from the given data. Estimate of beta naught is beta 1 hat. Estimate of beta 1 is beta 1 hat. Estimate of beta k is beta k hat. Error will go to 0. So finally, you will get this type of equation. Now you give any value to x1, x2, xk. You can estimate y. So it's an multiple regression is nothing but moving from simple regression to multiple means you are adding more and more independent variables. That's it. You are taking more and more independent variables. And in such type of situation, we compute what is called multiple correlation coefficient, rather than in simple regression, we simply look at R, Pearson correlation coefficient, because we are looking at linear relationship. So we compute that R. But in case of multiple regression, we compute multiple correlation coefficient. Now, if you do not look at, forget about what is happening after this plus, take only epsilon. So your data will be y is equal to beta naught plus beta 1 x1 plus epsilon. Then it reduces to a simple linear regression. Do not include x2, x3, xk, etc. Then it's a simple regression. So you can easily see that it is an extension from simple to k set of variables, and these are independent. A technique is same, everything is same. Now here are two important questions. What are two important questions? Number one, you are taking that y can be estimated based on x1, x2, xk. This is what you are presuming. This is your presumption. Now, do you think whatever the independent variables you have taken, they will predict y? Maybe out of this k, only, let's say k is 10. You are considering 10 variables. It may be possible that only out of the 10, 5 variables are important to predict y, 5 are not important to predict y. It can happen, right? And moreover, second point is that out of these 5, which one comes at number 1? That this is the most important variable to predict y. Which one comes at number 2? That this is the second most important variable to predict y, and so on. If I want to know that out of these k, only few of them are important, and in which hierarchy, which comes number 1, which comes number 2, then we apply another technique, and that technique is called stepwise regression. That technique is called stepwise regression. Once we follow the stepwise regression principle, it will include only those variables into the models which are making a significant contribution to predict y, and rest of them will be thrown out of the model automatically. Rest of them will be thrown out of the model automatically. And moreover, multiple regression will give you the idea, stepwise multiple regression will give you the idea that which one comes at number 1, which one comes at number 2, and which one comes at number last. So for that purpose, we apply multiple linear regression. Any question in multiple regression? Yes, please. Any question in multiple regression?
Sir, it's clear, but one question, how many k we can take in this multiple regression?
Depending upon your presumption.
Okay.
That y depends upon, so for example, yield of a crop. Yield of a
Yes.
crop depends upon rainfall. This you can
Seed,
consider.
fertilizer.
Yield of a crop depends upon fertilizer. Yield of a crop depends upon, let's say,
Seed.
type of seed orders, different quantity of the seed. It may also depend upon soil fertility. It may depend upon if you are giving some additional treatments of nutrition or some other product, right? So it depends
Yes.
upon that. These are the factors which you are including, that y should depend upon this. But let's say
for how many factors we can go? If 10, 20, 30, at least there should be some limitation.
Yeah, that's very important question. Very important question. That's why the researchers are required, because you are using your judgment, you are using your knowledge, that y is likely to depend upon this. Your judgment may be wrong also. That's why we go for stepwise, because if you have included unnecessary variables, then once you apply stepwise regression, they will be automatically thrown out of the model, that these are not necessary, although you have included them. You follow my point? For example, let's say yield of a crop. I know it depends upon rainfall, it depends upon soil fertility, it depends upon amount of fertilizer, it depends upon amount of seed. But let's say I also include the scores obtained by students. Do you think the yield will depend upon the scores obtained by students? Yes,
Sir.
it doesn't
No,
depend
sir.
upon. But if you include this variable into the model, it doesn't make any sense at all. Hopefully you will agree with me, right? It doesn't make any sense at all. And if it doesn't make any sense at all, why to include? So while choosing x1, x2, xk, you have to be very clear whether y can be predicted based on this or not. That's a research, that's a judgment a researcher has to put in. You follow my point? Hello? Hello? Yeah, you follow my point?
That was someone else. I have a small
Question.
yes, sir. Actually, multiple regression I've understood, sir.
Mhm.
I'm afraid, sir, I wanted to know something about Tobit regression, sir. But I'm afraid that is not included in the topic,
Yeah.
sir. Can you kindly
See,
just in a
okay.
briefly?
Okay. See, there are different type of regressions. This is called simple regression, multiple regression. Now, the problem of simple and multiple regression is they are applicable to the situation whenever dependent and independent variable, they are measurable quantities. All of them, they are measurable quantities. But sometimes the quantity may not be measurable. Let me give you an idea. Let's say coronary heart disease. Person is having coronary heart disease or not having heart disease. So that's your dependent variable. If they are having heart disease, it's 1. If they are not having, it's 0. Now, coronary heart disease depends upon number of factors. It may depend upon cholesterol level, that is X1, which is a measurable quantity. It may depend upon age, which is also a measurable quantity. But it may also depend upon gender, male and female. Now, it may depend upon sex also, but sex is not a measurable quantity. It's a categorical variable. It's a categorical variable. Either a person is male or a female, 1 and 2. Similarly, it may depend upon ECG, whether the ECG is normal or abnormal. It's 0 and 1. 1 means if it is abnormal, 0 means it is normal. So these are the situations where there is some variables which are categorical in nature, some variable which has measurable quantities. Now, all simple regression, multiple regression, all these regressions fails in such type of situations. When they fail, then what to do? Then we come across the techniques of logistic regression. In logistic regression, we have dependent variable as dichotomous. Person is having coronary heart disease, person is not having coronary heart disease. And these X1, X2, Xk, either they could be categorical variable or they could be measurable variables. Okay. Same thing is in Probit regression. Same thing is in Probit regression, where you can have a set of variables which could be continuous, which could be categorical. If you can include the combination of those, then those type of regressions can be worked out. You follow my point?
Sir.
Yeah. Is that okay? All right. Now, another important point, whenever we apply stepwise regression, we also get the value of adjusted R-square, which I'll explain you while giving you the practical demo. Now, here is an important exercise to you. There is line A and there is line B. If you see from your eye, which line looks smaller? A looks smaller or B looks smaller? Can anybody respond, please? Yes, please. No.
Sir,
A looks smaller. Absolutely right. If you see from your eye, A looks smaller and B looks bigger. All right. Now let's check your knowledge also. This is your A. This is your B. A and B both are equal. Actually, A and B both are equal. But when you see from here, A looks smaller and B looks bigger. What is the reason? Reason is very simple. Because if you see, A is closed from both sides and B is open from both sides. Yes or no?
yes, sir.
Yeah. Line is same. A, but only difference is A is closed from both sides and B is open from both sides. Let me tell you, human mind also works with the same logic. I am explaining the same things. If you are listening to me with closed mind, basically you are looking at line A. But if you are listening to me with an open mind, the same thing, you can have better knowledge, better understanding of the things. And what are the things I am explaining is the same thing. But you are focusing on line B rather than line A. That's why I have shown you this picture. Is that okay? Important point. So whenever you are listening to me, please listen to me with open mind. That's my request. Is this okay? Yes, please.
Yes.
Okay.
Yes, sir.
All right. Now we will go through R and RStudio. We'll go through RStudio basically. I mean, the interface of R is RStudio, but there are other statistical packages. And one of the important statistical package which people are using most of the time is SPSS. SPSS is a menu-driven package, and you will not have to write any program. You will get the output. Only thing is you need a little bit of understanding. Then there are other packages also. One of the packages called MATLAB. MATLAB stands for Matrix Laboratory. Matrix Laboratory means if you are dealing with the matrices, multiplication, or some complex type of mathematical multivariate type of techniques like factor analysis, cluster analysis, then MATLAB is very good. Minitab is another software which is generally used for power and sample size calculations. Statistica is a software which is used for data mining along with the SysStat. Statistica and SysStat, they are used for data mining. EpiInfo is a very, very important software. People from the medical sciences, they are using this EpiInfo. And EpiInfo, the advantage of EpiInfo is that there is no need to make questionnaire. You can record the questionnaire online. And once you click one or two buttons, you will get the entire Excel sheet of the data. For example, everybody knows about Google Form. Generally, we make Google Form. It just works like Google Form. There is a Google Form. You include your questions like what is your gender, male and female. Then what is your education? There are categories. You have to take one of them, and so on. And you will get the entire performa online. And you click one blick, your entire data sheet will be ready. That's EpiInfo. Enquiry is for calculation of the sample size. And in EpiInfo, you can do all type of calculations after that. You can compute mean, median, mode, skewness, kurtosis, correlation, regression, factor analysis, cluster analysis. Everything is available in EpiInfo once you get this data into the Excel form. SAS is a very, very important software, and most of the multinational companies, they are using SAS. R and RStudio, free softwares, right? And people are using this because they are open source softwares. Mathematica, people from those who want to do integration or differentiation, etc., they are using mathematics. StatGraphics is an important software where if you do some kind of analysis, let's say I apply a multiple regression model, then advice will appear at the end of the model that if you remove such and such variables, your model will be improved. Some advice, no other packages will give you advice except StatGraphics. BMDP is called biomedical data processing, which are used for biomedical experiments. Stata, people are using, economics people, they are using for growth rates and other things, economic growth rate, or everything is available in Stata also. Okay, SysStat, as I mentioned, it's available for data mining. S+, people are no longer using S+. Refined version of S+ is R and RStudio, basically. So all these packages, they are used in different situations. Most of them, they are paid softwares, including SPSS. But now it's the age of new era. People are focusing on Python. I am also started learning Python now. And if you have a good hand on Python, you don't need to learn any one of these actually, but it requires a lot of programming skills and other skills to learn Python. Okay, these are some of the references. The references will include, let's say I want to learn about linear statistical models, where they are applicable to which kind of situations. Then there is an important book by Bowerman and O'Connell. By Bowerman and O'Connell's book, very important book for linear statistical models. And right in the beginning, I discussed about the categorical data. If you want to master yourself on categorical data analysis, then there is a book by Alan Agrasti. Alan Agrasti's book is very good for categorical data analysis. There are different type of cancer prediction models, liver prediction models, which are given in this book. And very important book. I teach generally this course on categorical data analysis to our MSc or PhD students. Then there is a book which I'll recommend to each and everyone. I'll recommend to each and every one of the participants that you must go through this book, because some of you may not be from mathematics, and this book involves very little bit of mathematics. Biostatistics book by Wine and W. Daniel. It's a Wiley publication. This is a very, very important book where whatever the techniques I'm teaching, correlation, regression, then the one-way ANOVA, two-way ANOVA, repeated ANOVA, all these, they are given in this book. You don't require any other book, basically, for basic statistical techniques. Most of them, they are given in this biostatistics book. Even you can download the version today, right? Download e-version of biostatistics by Wine W. Daniel. You will get the entire copy today, right? Then if you want to master yourself on multivariate techniques like factor analysis, cluster analysis, conjoint analysis, correspondence analysis, or multi-dimensional scaling, then this is a very important book, Marketing Research by Naresh K. Malhotra. He is a foreign author, not an Indian author. And recently, in 2019, I have also written a book on, because I am working with the medical statistics, and medical statistics these I'm working with the doctors. I'm just right now having 8 to 9 projects, different projects with Government of India, WHO, World Health Organization, ICMR, Indian Council of Medical Research. All these projects are with me, and basically I'm training doctors for using appropriate statistical techniques. So like odds ratio, risk ratio, ROC curve, then techniques like multiple regression, correlation. These are important techniques which you will learn today. But techniques of meta-analysis, counting techniques, and all these techniques are given in this book. Mixed modeling, so they are given in this book. And this book was launched by International Medical Olympiad, which is right now the headquarters are in Greece. And it was launched by Greek people when they invited me, and they have requested me to write a book on medical statistics. And here I was when this book was launched in 2019, and people from 26 different countries, they participated in the launching of this book. And in the month of November also, again, I'm going to teach all these doctors and other people, and to give a training on medical statistics to these doctors. So this is, I think, the first part. And regarding myself a little bit, because hopefully I'll give you some idea what type of research I'm doing. Just a brief profile. See, can you see this page? Is it readable? Yes, please.
Yes, sir.
Yes, sir.
Yeah. So myself, Dr. Suresh Sharma, professor in the Department of Statistics, and I was the chairman from 2006 to 2009. And after that, I have become a coordinator of one of the important department of the university, which I was headed for almost 9 years, and that was Center for Systems Biology and Bioinformatics. So 3 students, they have done PhD with me during that time in bioinformatics only, and rest of them in statistics. And expertise area of myself is statistical modeling, and biostatistics, statistical genetics, and bioinformatics. I have a research experience of about 27 years. And these are the projects with me right now. One of the project is Public Health and Pollution Control in Asia, which is, in fact, this project is over now, which was funded by Health Effect Institute from Boston, US. Professionalization of youth work, it was funded by Commonwealth Secretariat, UK. Then I also work on dental caries. These 3 projects are still going on with me with Chandigarh administration. I'm professor in the Department of Statistics, Punjab University, Chandigarh. Then role of biomarkers. This project is also over now. This was also with one of the leading hospital, Government Medical College and Hospital in Chandigarh. Also working with many other projects which I have not listed here with WHO. WHO stands for World Health Organization. ICMR is Indian Council of Medical Research. I have written more than 130 research papers so far, and attended more than 37 international conferences abroad, and delivered more than 850 invited talks in India. So written several chapters in the books, and this is the book on medical statistics. These are some of the awards which I have. Best Research Award given by US Medical Research. Sorry, this was given by AIMS New Delhi. Then Wonder Wolf is Award USA, SG God Award, India, Shiksha Ratan Award, Best Citizen of India Award, Advisory Board Member, London School of Management Education, visiting professor I was in US with the National Institute of Health in US. Then again, I was there for second term. I was also appointed Ambassador Asian Council of Science Editors and also advisor to International Medical Olympiad. I have just shown you the picture. And Best Paper Award was given in the area of meta-analysis. And I also acted as a chief statistician for Global Harmony Project, Sweden and Russia. And one of the award with me is Anil Malhotra Award, which is generally given to people from psychiatry, psychology, and statistics. And then Excellence Award Research in Biostatistics. And these are the country I visited. 12 students, they have completed their PhD. 4 other are enrolled at present. And 4 doctors have completed their MS degree. And 1 doctor also has completed DM. And 3 people from bioinformatics have completed PhD. We have developed certain websites also. This is one of the website, which is called Cancer PDF, where all the related information, let's say somebody want to see what are the genes associated with the blood cancer, or what are the genes associated with the thyroid cancer, or let's say with the breast cancer. So all the information about those genes, what are their properties and other things we have compiled in this website that is called Cancer PDF. If you click on this website will open. Another website is this one, Disface, how to make full face from half face. This is another website which we have developed. For example, if somebody goes to the ATM machine and there is a camera on the left hand side, then only camera will capture only the left hand side. Then how to develop the picture from the half face to full face, not using camera trick, but by using bioinformatics approach. So very important, and people are using all these techniques. So that's my brief profile to you. If you still have any questions, and will take a break of about half an hour, I think, half an hour. And I'll be back at 5:20 with you rather than 5:30, so that we can finish by 7 o'clock rather than 7:30. And maybe by 6:45 even, if you will be with me. So if we can take a 20 minutes of break and come back, then I'll be with you around 5:15. Let's fix one time, whatever you suggest. Yes, please. Which time you suggest, 5:15 or 5:20? Just give me one time, please.
5:15 is okay, sir.
5:15 is okay. So we will be free by 6:45 or so for today's session. Will that be okay?
Okay, sir.
All right. So just take a cup of tea, or maybe you can relax a little bit. I will also take a cup of tea for 20 minutes. I'll be back at 5:15. And if you have any question, any query, you are most welcome.